So yes, good morning. I see everybody survived the lambada. So I will be talking about monitoring open source hardware. Most of the presentation is about open source hardware and why you should care. So quickly, who am I? So I'm from Belgium. I do a lot of enterprisey stuff. So most of the hardware I will be displaying is enterprise hardware, but again, you should care for other reasons also. I run a few conferences, so Config Management Camp. I help out with DevOps days. And once in a while I work also. And I'm also part of the Open Power Foundation, which you will hear mentioned a few times in the presentation. So like I said, I have a small introduction, more about open source in general. I know most of everybody knows what open source is, but I want to highlight why we should remain vigilant and care about open source in other spaces than just software. Then I'll go further to hardware. I'll be giving some examples, and at the end I'll say how that integrates with monitoring, specifically Isinga, because that's what we do. So open source software has been around for a long time, and in its actual word, it means that the source code is available. It means that you can read the source code. It means it's transparent. Multiple people can look at it, can think about it, and can actually understand what is happening. And then from that source code, depending on the licenses, you can actually build binaries, you can distribute the binaries, and there are a whole bunch of licenses around that. But that makes it very easy to implement and very easy to have your own version of this open source software. Isinga being a good example, you can compile your own Isinga. And if you want, you can make your own modifications specific to your environment, which makes it always very useful for companies to use, because while we all want to solve the same problem, the actual implementation of that problem might be slightly different for every enterprise. And so you can have multiple builds, but it also means that if you go to the Isinga website today and you download the binary, you can actually verify that that binary that was downloaded is the same like the source code. So you can do binary checks. You can verify that what you're getting is actually what is in the source code. And it is even possible to fork software. For those people who know Isinga a little bit longer, you will know that Isinga was a fork of Nagios originally, and then evolved to be better than Nagios. I think I can say that here. But the most important thing about that is there's diversity. That also means that you have the choice to do what you want. You see that with Linux distributions. There are thousands, if not millions, of Linux distributions. While typically people tend to use the most commonly used, it doesn't prevent you from starting your own Linux distribution, which we do actually in the company. And it allows you to choose which one is most appropriate for which workloads. So choice is very important. Now, I mentioned a few licenses. Typically, these are the major groups. There are many more than this. Public domain, which was originally the most commonly used one. So it's just there, and there's no exact license on what can be done, but you can do more or less whatever you want. The permissive licenses like Apache v2, BSD, MIT, which allow you to use the software for yourself, modify, and not give back to the community. And even though we have these permissive licenses, we see that those projects that use these permissive licenses still get a lot of contributions. If you look at the difference between the Linux kernel, which is a viral license, versus the BSD world, which is a permissive license, you still see a lot of BSD contributions. So big companies are still contributing to that. Then you have the viral licenses, so GPL, AGPL, which require you to contribute back. So if you make any changes, you have to contribute it back. It also means that all the Forks need to remain within the same licensing. You can take it in your, on your own and close it up. So that's one of the main differences. And then we have these two open core and the bullshit license, which are a little bit different. They create communities which are very diverse. There are a few projects which have tried to do this. Then you see forks coming up and things happening. So my presentation is mostly about the first three. I just wanted to mention that there are these other two ones which technically are open source because the source is maybe open, but there are a lot of features, a lot of limitations, so it doesn't help us in the long term. Now, if you look at hardware, this is hardware, by the way, for some people who don't remember what hardware is. And I specifically showed this model because this model is a very common model that was a proprietary firmware on it, but through reverse engineering, you can actually put core boot and other bootloaders on there. So you can open up the firmware on this machine. Now, if you go and look on the core boot website, you will see that there are maybe like 10 machines you can actually do that with. And most of these 10 machines are like 7 years old or older. So we have a problem where we have software which is open, but we are running it on proprietary hardware. And that's a huge problem if you look at these type of machines. Because these type of machines have so much embedded code in there that it's very difficult for anybody to understand what they're doing. You can have a very secure software stack, but if you run it on crappy hardware, you still have security flaws. And now, some of these major companies are finally realizing that they need to work in this space also. So we have all these hardware problems. Most of you must have had some interaction with some of them. But if you look at the first 6 of them, those are basically CPU defects and vulnerabilities within the CPU. And if this CPU architecture would have been open, you would have been able to have other people verify this and find it much quicker. The only reason that these people found it is because they were reverse engineering. Now, that's not a very good way of how the ecosystem should work. We should be able to look at the code, understand what it is, and find mistakes if there are any, and be able to apply our software knowledge and the learnings we have had in the software world in hardware also. And then we have a few other ones like the Intel Management Engine, which is basically just a spyware on most machines. And then you have the BMC, which is typically in the more enterprise machines, where you actually have a computer in your computer. So you have a little computer that bootstraps your big server. But we don't know what it's actually doing. And that's another problem. Initially, they open sourced the software stack, but again, ASP, being one of the biggest manufacturers, does not have an open source implementation in hardware. So the software on top of it already became open a while ago, but we still have this core that is doing something, but nobody really knows what it is doing. So the first thing that was open sourced is open firmware. You can find several projects on GitHub now. You have the ability to rebuild it and to upload it in the system. A few examples are Opal, which is used in the Power ecosystem. So it has host boot, OCC, ski boot, and petite boot as components. And you basically go to a GitHub repository. You can see the entire firmware stack. You can actually compile it because they have a project which is called OP build. You go to that, you clone it, you type make and the machine type that you want. And after some time, depending on your hardware, you will get a firmware that you can upload in a machine. And that is functional. Same for core boot. You can go to core boot, you can compile that. So on that ThinkPad X200, you can actually go to the core boot site, you can download it, you can inspect it, you can build it, and then upload it on the device. And like I said, many manufacturers are now understanding that this is a very difficult subject to crack, and they have come together under the OCP, so the Open Compute Project, and they have created what is called the Open System Firmware. So this is now a specification on how you should build your firmware and how it should be open sourced. And at the moment, there are only 2 manufacturers that actually comply with that specification. So IBM open sourced their Power 8 already in 2013. HP will be open sourcing theirs later today. It's American time, so it will be somewhere at the afternoon for us, which is why I have the question marks there, because the name might change. But they are now also opening up their entire firmware stack. And we know already that other manufacturers will start doing this also, which means that you can go and compile your own firmware, put it in the machine, and run those systems in that way. So this is one of those machines, and if you can see it properly, this segment is the BMC, which is the only part that was in that machine not open source. So this machine, the firmware is open source, everything is open source except that little device. And so together with a few other vendors, we are busy open sourcing this component, and I'll come back to that later in the presentation, but this machine basically can run fully open source software from the firmware. The BMC software part is fully open source if you buy it today, and if you wait a little bit, you will get a fully open source hardware component in there also. Which means that you can go to GitHub, download the project, manufacture the PCB board yourself, and put it in there. So what is open source hardware actually interesting for? We will open source the RTL codes, which means that you can download those, you can then build them and verify in a more software way before you put it actually in silicon, because once you put it in a board, yeah, you can't change it. It's not like software, so if you have bugs in there, you need to throw it away and build a new one. Which is why binaries are not that easy to build. So typically, you will have verification systems, you will have emulation that is done, but you won't actually go to silicon until you are sure you can do that. Which is why some of these projects are taking years to complete, because it's much more complex than software. We can't just push out things, because we need to be able to verify that. We need to be able to make sure that once we build that board, it is functional and it's workable. Which means that also having different implementations is very costly. You see that there are only a few firmware options at this point. If you want to do multiple builds, it means that you have more expenses. If you make modifications, you need to verify all those modifications. So it's much more complex. But it still allows you to have hardware forks in the sense that you can actually take the design and modify it to your needs and build it. So we need much more choice here. We need much more diversity here. And again, this is taking what we learned in the software world and converting it to hardware. And it's going to be much more complicated because hardware is a slightly different business. And the people doing hardware are much slower in wanting to change things. So what is the alternative to that? There's a soft hardware option. So this is basically today available, where you create programmable hardware. So in place of baking hardware like a PCB board or a motherboard, you create a FPGA, a field programmable gateway array, and you use that to then do your testing on. And so with one little board or with a bigger card, you can create and verify and test your soft hardware before you put that in actual silicon. This gives you the ability to make changes. This gives you the ability to use all of the software ecosystem and everything you learned within the software world and the tooling behind that on hardware. For the moment, the most popular soft cores are open power cores or RISC-V cores. They are all RISC-based cores, and they typically tend to target different markets. So open power is more the enterprise and the larger systems, while RISC-V you will find in a lot of the smaller systems. So for people that know the BeagleBone, it used to be an ARM processor. Newer BeagleBones you can actually buy with the RISC-V processor. And then the core itself is open. You can actually go to the website and see the schematics and the ISA and everything else in there. And then there are here a few other examples. There's a project called Litex, which gives you the ability to build that in a fully verifiable software stack that can be uploaded on this FPGA. And that gives you the ability then to do more verification, to use your software skills on hardware. One of these boards, this is a relatively cheap one, about 200 euros, and then you can start playing around. So you don't need to invest in a machine of 50,000 euros. A small one like this can already do a lot and run a full Linux distribution on it. And you get to choose which Linux distribution you'd put on that. This is a slightly bigger card. The difference between the two is mostly the number of LUTs, so the logical units. The more logical units you have, the more software you can put on it, or the more soft hardware you can put on it. Some of these cards also come like with network controllers, so you can actually build your own networking stack. And some of the high-end networking cards actually come with a Redis cluster in there or with an etcd cluster in there. So even manufacturers are using this more to be able to run software on hardware and then basically accelerate a lot of the workloads. So the idea is that we want to treat hardware as software, reuse all the lessons that we have learned and all the techniques that we have, follow the DevOps philosophy where we want to build things very quickly, fail, understand why we failed, and then learn from those things. And not have this silo where we have hardware being a separate thing and software. If we come together, we can actually work much better. We can create a CI/CD pipeline where we can do all of this testing, have it automated, so that we can figure out mistakes much, much quicker. So there are some other open initiatives, Open Road, Skywater. These are initiatives by big companies like Google, where if you come with a design, they will actually help you build it. So you don't need to invest like a few $1 million to get a silicon. They will help you out, and for a small fee, they will actually build it as long as it's open source. And the idea behind that is that if we now can get people involved in these projects, we can actually come to a state where open source hardware will be as good as open source software. So a few examples. I mentioned the BMC. So the BMC is actually the base management controller, where you IPMI against or you redfish against, and you start up your machine. So it's actually, or used to be, an embedded ARM processor, typically, or an embedded MIPS processor, which basically pushes a virtual power button on your machine, and then IPLs or boots up your machine. Now, that's actually fairly reasonable hardware to do stuff with. So we could actually use it for much more than just pressing a virtual power button or controlling the speed fans. So the first project is OpenBMC, which is quite mature by now. So many of the IBM, HP, and Dell machines that you buy today actually have OpenBMC running in the backend, which technically means that if you know which version, you can compile your own, have your own logos, make changes in how the BMC manages the fans, and how it will utilize maybe some of your GPUs, and you can make changes on that level. So that project is there. It's a Linux kernel with something called Phosphor, which is the actual BMC stack, and is built using Yocto. So it's a very small embedded system. And then the new project is called LibreBMC, and this is basically a hardware component where we're using the OCP DCSCM specification, so that's an open specification on how this board should look, how the connector should be, so that you can basically create that connector on a motherboard and then put it in a machine. And if it's an FPGA-based one, you can actually run your softcore, your gateware, which is basically the GPIO connections that you define. And obviously, companies like HP or IBM or Dell will create ASIC versions of this, which means that it's a more baked-in version where you will not always be able to run your softcore on, but it still means that that code will be available. You'll be able to verify that what is on the motherboard is what is actually in the code. And this prevents backdoors getting in there or the ET phone home problem with many of the machines. So you actually know that your machine isn't talking to some random thing on the internet. And that makes it very interesting for companies who need to be security aware and who want to prevent any of these vulnerabilities coming from these weaker systems. So here again, the example, that's the first machine I showed you. This is the components of the BMC itself that gets extracted, and then there's a DCSCM FPGA board, and using a network card, we were able to boot up the machine. So it's fully on GitHub. You can actually build this yourself. If you understand how KiCad works, you can actually go out and produce these boards yourself. An estimated production cost would be about 200 euros for such a little board. And obviously, once we get further and we can do higher volumes, we can make those costs come down. So there's actually two components, which is the interposer, because that connects to the motherboard. Given that this one had a different connector, we had to build an interposer, which also is on GitHub. So technically, you could build this yourself if you buy this machine. This is another example. So I showed you the RTA7, which is a off-the-shelf FPGA, and you could basically, with a breadboard, create the interposer and run it yourself. So if you want to do this now already, on many of the machines, you can actually bifurcate or bypass the BMC and connect your own BMC on it. And this is obviously a very small project for now. So we are looking on expanding this and moving to the next steps. So how does this actually fit in with monitoring? I mentioned the BMC. The BMC here basically is checking your system all the time. Because what is its job? Its job is basically to start up your machine, check the fans, check the hard disk, check the CPUs. Now, it's doing all of these checks already. Why do we want to have, on a higher level, Isinga connect and tell me how many hard disks there are, what speed they're rotating at, are they still okay, how much space is being used? Well, we actually have a component here doing nearly nothing except verifying all of this, but not giving that data back. Now, because we have all of these open source versions on that, we are able to embed Isinga now in OpenBMC. And I say work in progress because we have been able to compile it successfully on older versions, but it's not yet production ready. So we are working on getting Isinga in there. That means that you will get to know everything your machine does. You will be able to see which PCI cards are in there. You'll be able to see how much wattage it's using and actually verify all of this. OpenBMC also has MQTT, for instance, so you could use or enable that, and then have it send messages to your Isinga stack and get them already there. So this enables you to get very low-level access, but also limits the overhead. We don't need to stress the operating system or any other component, because this BMC's main job is to do this. So we're just asking it to give us this data so that we can use it ourselves now. And this gives us the ability to start monitoring hardware directly. It gives us also the ability to see when hardware will fail and prevent failure, and combine that knowledge with software. So it might be that your database is performing very badly because one of your disks is failing. Now, if you can correlate that data, you can understand better why these failures happen and how they happen. So yeah, we want to empower open hardware. Given that I'm part of the power ecosystem, I capitalize power. So yeah. Thank you. Any questions?
Yeah, you can talk. He will repeat your question for the crowd.
So you said most of the time it's sitting around doing nothing. A lot of simple hardware, it needs to be highly available for the tasks that it does. Is when you start adding on additional tasks like sending monitoring data via Isinga, is there a danger that it would then have too much workload doing the monitoring and not enough to do what it's doing, and then you'd have to up the CPU power of the BMC and the chain effect of having the BMC doing lots more work than it was initially designed for?
Yeah. So the question is, given that the BMC is a single component in some machines, how do we make it highly available? And is the stress level of adding monitoring on it going to increase failure? That's summarized. So the first step is, of course, making this open. The next step, and again, IBM has done this on some machines, is having 2 BMCs, so making them redundant. And if the cost is that low, it doesn't add anything on your total cost price. So that's how you can do it highly available. The bigger machines typically have 2 of them. So if you have like 4U rack servers, typically they have 2. You will also see that they are on opposite side of the machine. So the idea is also that in the future we would be able to add 2 DCSCM cards, and then it's up to you as a user to put 2 of them in. You can have 1 standard and optional second. So that's about high availability. And for the stress level, a typical BMC utilizes 0.1% of its resources. That's CPU, memory, and I/O, the limited I/O it does. So adding Isinga, for instance, in our tests have increased the CPU load to 5%, which is still under the 20% rule, so we don't see any problem in the long term. Obviously, if you're going to add like 5 different monitoring tools or 100 different things, yes, that might be a problem in the future. Now, the other thing is that many of these soft cores that we are using are very inefficient. So the next thing that we are actually busy is making them more efficient so that we can run more workload on it. But yes, this is another concern. But given that the project is so young, we started this about a year ago, we are not yet at that level. But that's definitely on the list of concerns. Any other questions?
If there are none, then there's nothing left to do but to give you a token of our appreciation for your talk and for spreading the open source ideology and knowledge.
Thank you.
Give it up once more for Toshaan.